academic, maybe a bit dry. But I think this is actually a fascinating example. It shows how you can find, well, real order hidden inside what looks like total chaos. Our source material basically lays out the attack plan for this polynomial we're calling P of. And when you first look at it, it seems completely intractable.
Intractable because
Mostly because it's coefficients.
yeah.
The numbers multiplying the powers of the px are just enormous, colossal.
Okay, so the mission then is to find the roots. Values of stick dollars that make this equation zero.
Exactly. For a simple quadratic, 6 by 2, 2, you expect two roots. Here, degree 12, you'll have up to three.
It's 12. And the starting number dimensions are a problem.
They're definitely a challenge. These initial inputs, the Kohlkircher coefficients, they're not like neat little single digits. I mean, the Kohlkircher is a constant, it's like 3 zeros. But after that, things get really fast.
How fast?
We're talking coefficients jumping into the millions, and then billions of zeros.
You mentioned $1,900 in the source. That one is $3,051,149,600. Just for one term. So these huge numbers are like the raw material. How does any system of find a solution?
Right, that's really where the deep dive starts, because this isn't just random number crunching. The whole analysis is guided by a specific framework. Right, it's called Mourad Sultan Ezouidi's Theorem. Think of it as a powerful algebraic engine designed for exactly this kind of situation, simplifying high-degree polynomials if they have certain hidden structures.
So if polynomial is this amount of like a specialized piece of equipment, an excavator.
That's a good way to put it.
Yeah.
But it's not just digging random. It knows where to look.
Numbers into some giant
It relies on structure. And this is the really interesting part. The source highlights again and again. The theorem's elements are deeply rooted in combinatorics.
combinatorics, like counting principles.
Exactly. It uses patterns you find in things like Pascal's triangle. Specifically, the coefficients from the 11th row, 1, 12, 5, 5, 165, those numbers.
Okay, hang on. Pascal's triangle. That usually comes up with like expanding a plus b, right? I know.
Precisely. And the fact that combinatorics is baked into the theorem tells you something important. It means the theorem isn't really bothered by how big 3.3 billion is. It cares about the relationship between that coefficient and the other. It's looking for a pattern related to how powers expand, sort of a hidden counting symmetry within the polynomial itself.
So the input coefficients, that would seem like huge. But the theorem applies this combinatorial formula systematically calculated across all terms. Right up to
That's the process. And the output of all this calculation is a new set of coefficients. Let's call them score estimates.
okay.
And this is where things get, well, really unexpected. We built up this picture of a giant messy equation. Now we apply the theorem.
What happened?
This leads us to what the source calls the vanishing point. Because honestly, after expecting immense complexity, the result is almost silence. How massive is this theorem? You start with this 13-term polynomial defined by those billion plus coefficients.
Yeah.
You apply the theorem systematically.
Yeah.
And the resulting polynomial, defined by the least added coefficient, it sheds nearly every single term, almost all of them zero.
Wait, zero. How many? Zero.
Here's all of them.
Okay.
Also zero. 6, 3, 1. Zero. All gone.
And that's 5 terms.
And it doesn't stop there. You just have to know 6, 6, these 0, 17, there's 0, 6, 10, there's also 0.
Wow. So that's 5 more. 10 coefficients in total just vanish.
And calculating coefficients is perfectly to 0. Quite dramatic.
So out of the 12 possible terms we could have had coefficients for, besides the sixth term itself, 10 of them are gone. Leaving only 2 survivors, 2 non-zero calculations.
The survivors are 6 pounds and ocean plus.
And are they small now?
Oh no, there's still huge numbers in their own right.
Yeah.
There's involved 126 numbers. But they're isolated.
Conceptual. It wasn't just defined
He reveals the cancel with the 12th degree directly. We can just say 11 is by $67. And if AI was by $60, then $6 is just $14.
Big difference. And suddenly, that beast of an equation becomes $y is 11 plus a is $6 and b is 12.
Wow. So it just becomes a standard high school quadratic problem.
Fundamentally, yes. All that heavy lifting that Theorem did, all the combinatorial machinery, was all to clear away the debris and show us this underlying quadratic system.
That's the payoff. The algebraic difficulty just evaporates.
It does. The theorem did the hard work to eliminate those 10 terms. They were simply substitutes.
Okay, so the structure is simple now. But we still need the actual roots, right? All 12 roots. How do we get that?
Well, we solved that quadratic equation for $8, which means we're solving for $6.
Using the good old quadratic formula.
Pretty much. So again, the number involved is the source is here in the it involves a number around 190. So yes, the process is straightforward and quadratic. Okay, quadratic formula gives us two possible values. That means two possible values. If 6 L's is a number, how do you get $6? You need to take the 6.
Taking the sixth root of a number doesn't give you just one answer.
Right, it gives you 6 answers. 6 complex.
Precisely. For each of the two values we find, 6 or 6, taking the sixth root generates 6 distinct solutions for 6. Geometrically, they form a hexagon.
6 roots in the first solution, 6 in the second. That gives us 12 roots.
That's how we get all 12.
And the source is the final formula. Are they simple?
Well, simple might be pushing it. They look complicated, but they have a clear structure. Interestingly, they all relate back to that very first coefficient we saw.
The del dollar cube equals 244.
That's the one. It acts as a sort of anchor point. Each root is basically 24 plus or minus 1 of the complex 6 roots derived from those giant 6 algebra values we solved for.
Ah, so the formula has that structure. 24 plus something involving the 6th root, and the 6th root part brings in the complex numbers.
Yes.
All right, today we're going on a bit of a mathematical detective journey. We've got this one mission, to solve what looks like an absolutely impossible problem. I'm talking about an equation so complex, it's basically a monster. But, you know, as we're about to find out, sometimes the biggest monsters, well, they're hiding the simplest secrets. Okay, so let's just dive right in. Meet our monster. Yep, this is it. It's a 12th degree polynomial. All that really means is that the highest power of x you see there is 12. And even this is just the beginning of it. Those dots mean it just keeps going. The coefficients are huge. It is, no joke, an intimidating beast of an equation. It's the kind of thing that's practically designed to make you just, no, close the book and walk away. I mean, seriously, just look at it for a second. Where would you even begin? This isn't your standard high school quadratic equation, right? This is on a whole different level. It's a puzzle that honestly seems to have no starting point at all. So when you're up against a really specific, really difficult lock, you don't just start jamming random keys in there, right? No, you need the key, the one that was designed for it. And for a problem this unique, we need a secret weapon, a tool that was built for exactly this. And here it is, Mourad Sultan Ezouidi's theorem. Now don't worry, we are not going to get bogged down in the nitty-gritty formulas of the theorem itself. Just think of it like a powerful diagnostic tool. It's our recipe. It's going to let us test every single piece of that monster polynomial and figure out what it's actually made of. And speaking of recipes, here are our ingredients. The coefficients, you know, all those huge numbers from our monster equation, that's what we're going to feed into our theorem, one by one. It's time to start the investigation. Okay, so the investigation begins. What the theorem is going to do is take all those ingredients, those original coefficients, and it's going to spit out a whole new set of values. We'll just call them S coefficients. And you can think of these as like a simplified readout of the polynomial's real structure. Our job, as the detectives here, is to look at these new values and see if we can spot a pattern. All right, first test is done. We run the numbers through the theorem, and our very first S coefficient, S0, it comes out as 0. Okay, interesting. One component down. What's next? Second test, also 0. Okay, wait a minute. Now we might have something. Is this just a coincidence, or are we starting to see a pattern here? And the third result is in. You guessed it, it's 0. Again. Okay, this is getting weird. We have this absolutely massive, complicated polynomial, but our super powerful theorem keeps telling us its essential building blocks are nothing? What is going on? And yeah, the pattern keeps going. The next two S coefficients, 0 and 0. So that's 5 tests and 5 zeros. It's almost starting to feel like this whole monster equation is just some kind of illusion. But then, just when we're ready to write this whole thing off, our investigation takes a sharp, dramatic turn. That pattern we've been watching so carefully, it's about to be shattered. Boom, there it is. The fifth S coefficient is not 0. And it's not just not 0, it is a massive number. This is the plot twist, right here. After that long string of nothing, this enormous value just pops out of nowhere. This is the proof we needed. There is something real, something significant, hidden inside this equation, after all. This is our first big clue. But just as suddenly as it showed up, the signal's gone again. After that one huge number, the next 5 tests, 6 all the way through 10, they all go right back to being 0. The silence is back. And honestly, that just makes that one number that survived feel even more important. And then, right at the very end, the last test, we get one final survivor. A second, absolutely enormous, non-zero number. So let's just step back. Here's the crucial point. Out of 12 possible pieces of this puzzle, our theorem has basically vaporized 10 of them. It left just 2 survivors. And these are the only parts of the entire equation that actually matter. So now we have everything we need. With just those 2 surviving numbers, we can finally crack this thing open. It's payoff time. Let's see what this whole investigation was all about. And this just perfectly shows the power of what we just did. Look at that. The monster on the left, with all its scary, complicated parts, it just collapses because 10 of its core components turned out to be 0. It simplifies down into this beautifully clean equation on the right. And it's built using only those 2 giant numbers we found, our 2 surviving clues. That's it. I mean, just let that sink in for a second. The theorem didn't just help us solve the problem, it completely changed how we see it. It revealed that the problem was actually simple all along, just disguised in some very complex clothing. All that noise, all that mess, was just hiding a simple core structure that's defined by only 2 numbers. So from here, the path forward is actually pretty clear. Now, yeah, finding all 12 solutions or roots, it's still going to take some calculation. But it's not an impossible task anymore, not even close. The monster has been tamed. The puzzle is now totally solvable. And it kind of leaves you with this really fascinating thought, right? What other monsters out there, and I'm not just talking about math, but in any field, what other monsters are really just simple problems in disguise? All they're waiting for is the right tool, or maybe just the right way of looking at them to finally reveal their secrets.